During the Cold War, the United States briefly entertained the idea of protecting themselves from nuclear attack by nuking space. No, this isn't the plot of some 90s popcorn blockbuster, although it probably should have been. Between 1958 and 1962, the US conducted a series of nuclear tests designed to answer the question, could a high-altitude nuclear explosion provide a defensive or tactical advantage in the event of a nuclear attack? Welcome to the door to the universe. Remember to subscribe to the channel and we'll get right to the good stuff. So, how exactly would detonating a nuclear weapon in space defend against a foreign nuclear attack? Well, the simplest answer to that is geomagnetism. At its center, the Earth has a solid iron core. Surrounding the solid core is a molten core, which spins and rotates around the solid one. This motion effectively turns the entire planet into a giant electromagnet. That magnetic field extends out into space, and it is incredibly important to maintaining life on Earth. The geomagnetic field creates a sort of flow on the atomic level, similar to an air or water current. This flow, combined with the power of gravity, is largely how Earth is able to maintain its protective atmosphere. But that magnetic current doesn't just help keep our atmosphere from floating off into space. The shining star of our solar system is constantly assaulting us with ultraviolet light, bathing us in ionizing radiation. This is where the geomagnetic field comes into play. The oxygen in the upper atmosphere filters out most of the ultraviolet light before it reaches the surface. However, these rays do still ionize atoms in the upper atmosphere when they can interact with it. The loose electrons fall into the currents of the field and are subjected to something known as the mirror effect. This is where recently freed electrons become trapped in a back and forth bounce until the excess energy is dissipated. In layman's terms, the mirror effect makes the ionized rays run laps until they tire themselves out. We can actually see evidence of this very process in the northern and southern lights. The beautiful dancing colors visible in the night sky near the poles are the result of the geomagnetic field keeping us safe from the giant nuclear furnace at the center of our solar system. Nicholas Christopoulos was a Greek physicist who, in 1957, after considering the effects of a 1-megaton fission bomb, theorized if a nuclear fission device was detonated in high enough altitude, the mirror effect would spread the decaying radiation over a large path, creating a blanket over the designated area. This blanket could potentially be used to disable incoming weapons or knock out the radar systems in the given area, depending on how it was deployed. Intercontinental ballistic missiles are launched into space, where they utilize the rotation of the Earth to reach a target on the other side of the globe. When the Earth is turned enough for them to get to where they intend to go, they re-enter the atmosphere and kaboom! The newly coined Christopoulos effect would utilize both the disruptive power of the electromagnetic field created by the detonation, as well as the Earth's natural mirror effect to melt, short, or otherwise disable the triggers and guidance systems of an enemy warhead re-entering the atmosphere. This would render the nuclear element of the weapon effectively useless and therefore avert a radioactive crisis. Upon closer study, detonation points, known as the magnetic conjugates, for both offensive and defensive uses of the Christopoulos effect were determined. The offensive belt would need to have a conjugate in the Indian Ocean, while the defensive belt would require a conjugate in the South Pacific region. When these conjugates were determined, official testing by the Department of Defense began. The first set of tests of the Christopoulos effect were known as Operation Hardtack. They were conducted at the Pacific Proving Grounds between April and August of 1958. During the 5-month span, 35 high-altitude nuclear tests were conducted. Nuke was the first high-altitude test performed. Every element of this test was monitored, from the force of the detonation itself to the effect it would have on the ozone layer, and, of course, the potential of the Christopoulos effect. The test held a yield of 1.7 kilotons, just over 1/10 of the size of the bomb that was detonated over Hiroshima. Nuke was detonated at a height of 86,000 feet, or 26.2 kilometers. The shockwave from the blast took over 3 minutes to reach the aircraft carrier that launched the bomb. From there, the testing was on. Operation Hardtack was immediately followed by Operation Argus, which ran from August 27th to September 9th of the same year. While Hardtack conducted high-altitude detonations, Argus took things even further to the edge, with their lowest detonation occurring at 110 miles, or 170 kilometers. All of these tests occurred in what is known as the thermosphere, or the second-to-last layer of Earth's atmosphere, and beyond what is known as the Kármán line. The Kármán line is understood as the official edge of space, at 62 miles or 100 kilometers above the surface. 99% of Earth's atmosphere exists below it. The lowest Argus test was conducted at nearly twice that height, and the furthest test was conducted 8 times that distance at 493 miles or 794 kilometers. Argus was particularly interested in seeing how the Christofilos effect worked and documenting how long it would be, well, effective. This series of tests was conducted in the South Atlantic, 1,100 miles or 1,800 kilometers southwest of Cape Town, South Africa. Project Argus resulted in a verifiable shell of electron radiation, validating the work of Christofilos and providing a massive wealth of data on the phenomenon. 4 years later, Operation Fishbowl continued the high-altitude testing begun by Hardtack and Argus, but was far more controversial. Fishbowl had fewer tests than its predecessors, but it had far more failed tests, with the Thor rocket system having several fires and premature explosions both on the launch pad and in the air. The most notable test, Starfish Prime, detonated successfully, but had a much larger electromagnetic pulse than anticipated, causing not only electrical problems within the testing instruments, but overloaded telephone systems, set off burglar alarms, and knocked out 300 streetlights in Honolulu, 900 miles away. While Fishbowl conducted several tests after this, Starfish Prime let both the American public and the world know what the US military was up to. The public unease over tests such as these, both in the United States and in Soviet Russia, led to the partial nuclear test ban treaty 1 year later. France and China continued to test weapons above ground for a while the United States, United Kingdom, and USSR ceased all above-ground nuclear testing. Today, above-ground and high-altitude nuclear tests are beyond unthinkable. The number of satellites orbiting the Earth that would be directly affected by nuclear testing is significantly higher than it was in the 1950s and 60s. Using the Christofilos effect as a nuclear defense system in this day and age is simply out of the question. The impact it would have on communication, transportation, and general electrical functions would make the protective blanket provided by the phenomenon more of a problem than a solution. So while the data collected from the tests is absolutely fascinating, its usage will have to remain, unfortunately, a Cold War relic. Thanks for watching. Don't forget to tap that like button and check out one of our other videos next, where we will once again walk through the door to the universe.